Hey pre-calc friends, it's a great evening. I had a great dinner, the weather's nice. I saw Allison Thompson at the baseball game. There's your shout out, Allison. And maybe most exciting of all, we are doing our last lecture for the year. And so today we're getting into 11.5, which is talking about the area problem. And there we go, my laser wasn't working for a moment. But basically, we talked about derivatives earlier in this chapter, and after derivatives, kind of the second basic question of calculus is dealing with areas. So we will often see we will be given a function, and it will ask us to find the area under that function that is bounded by some vertical lines and the x-axis. So we can kind of see that this shape here does not form an area formula that we're used to if we had a triangle or a rectangle or any of those geometric shapes we learned in our past math lives. We could do that pretty easily, but we can see this is a really weird shape. So we're going to start with just trying to approximate what this area looks like. And the first few suggested problems in your homework are going to be similar to this. So it says, approximate the area of the region bounded by the function f of x equals 2 minus x squared, the x-axis, and the lines x equals -1 and x equals 1 using the indicated number of rectangles of equal width. So in this problem, there are 4 rectangles. So I already drew these out for you, and it's telling us they are of equal width. So some things that I just want to quickly kind of talk about is we know that the area of a rectangle is the length times the width. Okay, so basically what we need to do here is find the area of each specific rectangle and then add them together. And if we look at these rectangles, you guys may see like this red space that is under the curve, but we're not really talking about, okay? Because this rectangle does not cover that space. This rectangle, if I can talk, does not cover that space. But we also notice on the other side, our rectangle covers some space that is not underneath the curve. So that's why this is approximation. I'm hoping that this area and this area are pretty equivalent, and same with this and this, that they'll kind of even themselves out. Okay, so we're going to go ahead and look at each rectangle individually and find the areas. So I'm doing an extreme close-up here, and the first thing that I just want to point out is that if these are all of equal width, and it's going from -1 to 1, and there's 4, that means that each of these needs to be 0.5. Okay, so basically what we're doing is we're taking this total distance, which in this case is 2, and dividing it by the number of rectangles. 2 divided by 4 is 1/2. So that's how we're figuring out this width. Now, to figure out the height of each rectangle, what kind of stands out to me is that the y value on the right side of the rectangle actually touches this function. Okay, so what we're going to do, I know if I substitute in an x value into our equation, it will give us a y value. So we're going to have to look at each of these separately. So I'm going to call this rectangle 1, rectangle 2, rectangle number 3, that green is kind of rough, and then let's see, rectangle number 4. So if I'm starting here with rectangle number 1, okay, I'm going to try and find this spot right here. So I can see that this x value is -0.5 because it's going to the left 0.5. So in order to find that point right there, I'm going to do f of -0.5. Okay, we know that our function is 2 minus x squared. So I'm going to do 2 minus -0.5 squared. So I get 2 minus 0.25, which is 1.75. So the area for rectangle number 1 is going to be 1.75 times 0.5. So we get that our area here for that first rectangle is 0.875. Okay, so up at the top here, I'm just going to say area equals, that first one is not 1.75. It is 0.875. Okay, so that is my first area. Okay, so now we're moving on to our second rectangle, which is right here. And this time, it looks like my height, I'm going to use this point, which looks like it would be f of 0 because it has an x value of 0. So I'm going to do 2 minus 0 squared, which is 2. So the area would be 2 times 0.5, which gives us 1. So I'm going to go ahead and up here, I'm going to add plus 1. Okay, next I have rectangle number 3, which is right here. Okay, it looks like this point is at 0.5 because it's going 0.5 to the right. So I end up doing 2 minus 0.5 squared, which I notice is 1.75. This is exactly the same area, or I should say the same height, as the rectangle that was at negative 0.5. So our area would be 1.75 times 0.5, which is 0.875. So I'm going to go ahead and add 0.875 to my area. Lastly, I have this last rectangle, rectangle number 4, and this is the point which is actually at 1. So I'm going to do f of 1. So 2 minus 1 squared gives us 1 as the height. So the area would be 1 times 0.5, which is 0.5. So when I'm going to go ahead and move up here, I'm going to add on 0.5. There we go. And now we actually need to add all these terms together. And I end up getting 3.25, okay, and I'm going to say square units. If you guys abbreviate that, that's totally fine. Okay, but that is what we are saying is this specific area under the curve here. Now, what I want to point out, this next question, it says, what effect would using more rectangles have on finding the approximation of the area? And what I want you guys to realize is that if we had more rectangles in here, there would be less space that is not actually under the curve. We would really cover more of that area. So I'm going to write that it would be more exact. In fact, in honors pre-calc, we spent a lot of time actually finding the sum as the number of rectangles goes to infinity. And good news for us, we're not going to do that. In fact, I want to stress right now, we are not doing this the way the book teaches. We are teaching you something different. So if you try and check your answers on Calc Chat, you are not doing it the way that I'm teaching. Okay, we're actually learning a shortcut which should make us all happy. So what we just did was not difficult, but we can kind of see that in order to be exact or be closer to exact, it would take me way more time if I'm adding a ton of rectangles. Imagine using that process if we found 10 rectangles or 50 rectangles or 100 rectangles. It would take forever. Okay, so in order to find the exact value under the curve, we're going to use what we call the fundamental theorem of calculus. And that sounds really important to me. It'll be utilized a lot in the first year of calculus. And today I want to stress that we're really just doing a brief introduction of this. We're not really going into why this works or being super specific in why we do certain things with the notation, but we just want to see how can this help us out. Okay, so it says if f is continuous on the closed interval from a to b, then f is the indefinite integral of f on the interval. Okay, so what I want to show us, this is actually what we call the fundamental theorem of calculus. So it's saying, okay, if we're finding an interval from a to b of a specific function, and this dx, the reason why we have it, and I'm not really going to go into detail on this, but it really is defining which variable are we integrating. Okay, so in this case, it's telling me that we're integrating x. This notation, this capital F, is showing us that it is an integral. And the indefinite integral, often we will call this the antiderivative, because it's like the complete opposite of what we did to find a derivative. You guys may remember we learned what we called the power rule, where we moved exponents out in front and we dropped exponents by 1, and that was our shortcut. So to find an indefinite integral, what we're going to do, I'm going to bump my exponent up by 1 and divide by my new exponent. Okay, so I just want to do a few of these off to the side before we get into real problems. So let's say we had something like 3x squared minus x dx. Okay, so if I'm looking at this first term here, I'm going to say capital F of x. So that means the integral of f of x is going to be 3x, and I'm going to bump that exponent up 1, so it's going to be, instead of 2, it's 3, divided by our new exponent, which is 3, minus x, I'm going to bump it up 1 to squared, divided by my new exponent, which is 2. So I get f of x equals x cubed minus x squared over 2. Okay, so we're kind of noticing it is super repetitive. Okay, let's do another one. What if we were finding the integral of 5x minus 2 dx? Okay, so f of x equals 5x, we said we're bumping the exponent up 1, so from 1 it's going to become a 2. That was really ugly writing on my part. And I'm going to divide by our new exponent. And this next one's kind of tricky because I don't see an x, but we know that it's really like I have x to the 0 power. So if I'm bumping that up 1, it would become x to the first power divided by 1. So I get f of x equals 5x squared over 2 minus 2x. Okay, super, super repetitive. The more we practice it, the better we get at it. Let's do one more. Let's say I had 2x to the 4th plus 3x squared minus 5 dx. Okay. So, f of x would become 2x to the 5th divided by 5 plus 3x cubed divided by 3 minus 5x to the 1st divided by 1. So I'm going to get f of x equals 2x to the 5th over 5 plus x cubed minus 5x. So that's just something good for us to practice to make sure that we understand how to do that concept. Okay, so if we actually get into example number 2, it says, find the area of the region bounded by the graph of the function and the x-axis over the specified interval. Okay, so it tells us f of x equals 3x plus 2, and the interval's from 0 to 2. So not that we need to do this, but just to give us kind of a picture of what this graph is going to look like. Okay, I know I'm finding, it says from 0 to 2. I'm finding all of this area right there. Okay, so we're going to say the integral from 0 to 2. So we always do where we start, that's like the lower limit, and where we end is the upper limit, of 3x plus 2 dx. So I need to start by finding out what is the indefinite integral. So for 3x, this would be 3x squared over 2, and 2 would just become 2x. So from this point, I need to do f of 2 minus f of 0. So 2 comes from that's where in our interval we're ending. 0 comes from that's where we are beginning. If you guys accidentally switched those two, you would end up with a negative area, which would tell us we are wrong. Okay, so I'm going to do 3 times 2 squared over 2 plus 2 times 2 minus 3 times 0 squared over 2 plus 2 times 0. So what I did there is I substituted 2 in for x in our integral, and then I substitute 0 in for x in our indefinite integral. So when we simplify this, okay, I get 4 times 3 is 12. 12 divided by 2 is 6 plus 4. So I get 10 minus, when I simplify this, we get 0. So my answer is going to be 10 square units. And that is an exact answer. So that's all we would need to do. Okay, we're actually only going to go through one more example. We're going to find the exact value of the area of the bounded region from example number 1. And so we would say we're finding the integral from -1 to 1 of 2 minus x squared dx. So first thing that I'm going to do here is I'm going to figure out, okay, what is f of x? So it would be 2x minus x cubed over 3. So f of 1 minus f of -1. So with this, I know that we need to substitute into the indefinite integral. So I have 2 times 1 minus 1 cubed over 3 minus 2 times -1 minus 1 cubed over 3. So if I'm doing my work here, I get 2 minus 1/3, which gives me 5/3, minus, okay, and this should be a negative. I don't know why I didn't write that. -2 minus 1/3 would be like -2 plus 1/3, which would give me -5/3. So when I add these, I get 10/3 square units. And if you guys actually found out what this is, this would be like 3.3 repeating. And if you guys look back to what we found when we approximated, we got 3.25. So we actually get something that is pretty similar. So most of your homework tonight is going to be like 2 and 3, where it is giving us a function and giving us an interval, and this is the method that I would expect you guys to use to solve it. So enjoy. Signing out for the last time. I hope you enjoyed our lecture today.